Welcome back, everybody. Today we're going to be doing our two last microminerals. So we're going to be talking about iodine today and fluoride as well. So yeah, these are the last, it's basically the last lecture of the entire course. So what is the main function of iodine in the body? Where have you seen this before? So basically, iodine is pretty much solely involved in making thyroid hormones. So it basically, we absorb it and it travels straight to the thyroid gland, and then it's only the thyroid gland that really uses it. So yeah, it's pretty much thyroid hormones. And then this one's probably a bit easier. What does fluoride do? Fluoride, obviously, we use it for like maintaining teeth, that type of thing, reducing incidence of cavities and stuff like that. So iodine in the body, we actually have pretty small amounts, just 15 to 20 milligrams. And then just to point out that it's found in its iodide form. So that's the kind of -1 valence state. So yeah, we call it iodide in the body for the most part. Food sources, we primarily get it from iodized salt. That's the main thing, and we didn't used to add iodine to salt until I think it was like the early 1900s, and I'll go over the history of that. And that was basically to prevent goiters, and we're definitely going to talk about that. But you can find it naturally in seafoods, particularly fish that come from the sea, so not really lake fish. And then it's found in a whole host of other things, like moderate amounts are in like dairy, meats, and some vegetables and beans and stuff like that. But the main place we get it is iodized salt. And most salt is iodized. So stuff that isn't iodized is like, what is it called? Just like typical sea salt. If you buy that, that usually doesn't have iodine in it. But any of the kind of just straight up Morton's kind of salt is pretty much always iodized. So the amount of iodine varies greatly in the soil content throughout the world, and the amount of iodine in drinking water is an indicator of soil content. And so that also, the amount that you have kind of in water and soil would then parallel incidence, obviously, of deficiency, so of goiters. So basically, when you have a lot in drinking water, so in the US and in Delhi and India, you don't see goiters there. Whereas in places like Nepal, they have very low amounts in their drinking water, and then you actually still see a lot of goiters in that country. And I mentioned it briefly, but yeah, just to point out, seafood has high iodine content because marine animals can concentrate iodine quite well. And then seawater fish provide much higher amounts than freshwater fish. So for instance, tuna from the sea would have about, up to like 300 micrograms of iodine per 100 gram serving of that food. And then freshwater fish would only have like 2 to 4 in comparison, in the same 100 gram, excuse me, amount of that product. When we eat iodine in foods, we eat it as either that iodide form, and then sometimes it also comes in the food as an iodate form, and that's when those 3 oxygens are attached. We can also actually consume it. It can be bound to amino acids as well. And then it can also just be straight up in the form of thyroid hormones. So remember, the two main thyroid hormones are T3 and T4. And then so when we consume iodine, similar to everything else, basically we use proteases in our stomach and small intestine to liberate the iodine from those proteins, from the amino acids. If we happen to take the iodine in that iodate form, we basically need to reduce it down to this most basic form of iodine by glutathione. And then T3 and T4, if anyone in the class takes thyroid hormone, you probably know that those are just absorbed intact, so the body doesn't break down those hormones. It can really just be, I'll show you in a couple slides. They just go right in, basically. So looking, the, sorry. So iodide absorption is, primarily in the small intestine and the stomach. And then after digestion, so after we cut that stuff off, the iodide is absorbed really rapidly through passive diffusion. And we basically, take in almost 100% of it. So it's not really complicated. So many other minerals had like that whole pattern of kind of at higher intakes it's passive diffusion, and then at lower intakes it's energy dependent. Well, iodine doesn't follow that at all. Basically, our body really readily takes it in, just pretty much always by passive diffusion, and almost 100% is absorbed. And then in terms of thyroid hormones, those, as I mentioned before, are absorbed intact, and that's also done by passive diffusion. So that's why, for anyone taking thyroid hormones, your body can absorb them. And we absorb about 75% of those. With thyroid hormones, you're supposed to take them basically early in the morning, and then not eat for about an hour afterwards, just so it doesn't kind of interact with anything else. So iodide and then and T3 and T4, after they're absorbed, are transported to tissues in the free form, and then the majority of this is taken up by the thyroid gland. So just to point out, no other tissues that we're aware of, no other organs use iodide. The only place that iodine goes, or iodide, is the thyroid gland. And then just remember the thyroid gland's that kind of like butterfly-shaped gland that we have kind of sitting, right above our collarbone, kind of wrapped around the trachea. So pretty small little thing, just kind of wrapped there. And then so in the iodide form, the thyroid would take that in through sodium-dependent transport. And then the actual T3, T4, so those thyroid hormones, would just enter the thyroid via endocytosis. And then, basically we do have some iodine kind of circulating around, obviously, but again, it's just the thyroid gland that really uses iodine. So I also want to point out something that can kind of interfere with basically something that competes with iodine. It's something called goitrogens. So these are substances that compete with iodine for active transport into cells. And goitrogens basically can be found in like cabbage and kale, cauliflower, kind of the green and leafy things for the most part, but also in like turnips, cassava, stuff like that. And basically what they do is when you ingest a lot of goitrogens, they can result in less uptake of iodine by the thyroid gland. So basically they kind of release these chemicals that circulate around, and they'll actually compete with iodine to get into the thyroid gland. So people that take in like really high amounts of these things, and I was trying to look at the exact level, but if you're taking in super high amounts of this, it can actually lead to some thyroid issues. So if you were ever diagnosed with thyroid problems, and if you tend to eat like tons and tons of salad, it could actually like interfere with your thyroid gland production, or sorry, thyroid hormone production. So the key function of iodine, so the nice thing about both iodine and then fluoride, basically there's just one function each. And so, not surprisingly, the function of iodine is to synthesize thyroid hormones. So T3, remember that one is triiodothyronine. And then the other hormone is T4, which is thyroxine. And thyroid hormones play a ton of roles around the body, mainly in growth. So like increased protein synthesis, they help with long bone growth, they promote the maturation of neurons, and then importantly, you probably heard about this one before, it's probably one of the main ones that people remember with thyroid glands, it does regulate basal metabolic rate. So people that are hypothyroid have basically they're not making enough thyroid hormones. They tend to have lower basically metabolic rate, and then they tend to gain weight. Whereas if you're hyperthyroid, people with hyperthyroidism tend to release too much T3 and T4, and then that basically they're metabolic rate kind of jumps up, and then they tend to kind of lose a lot of weight. So you've probably heard about, yeah, thyroid hormone disorders and how it affects body weight. So yeah, just to walk you through kind of how iodine is incorporated into thyroid hormones. So here's T3 and here's T4. This is what they look like. T3 is called that because it has 1, 2, 3 iodines on it. So yeah, that's why it's called that. And then T4, not surprisingly, is called T4 because it has 1, 2, 3, 4 iodines attached. And then I just want to show you too, there's monoiodotyrosine. So that is a precursor, and same with diiodotyrosine. So these two are precursors to making T3 and T4. And then not surprisingly, the monoiodo has 1 iodine on it, and then diiodo has 2 iodines on it. And then also to point out, this thing, everything but the iodine, is called thyroglobulin. So thyroglobulin is basically this big compound here that the iodine sticks to. So yeah, that's also thyroglobulin. All right, so let me just walk you through how thyroid hormones are made. So iodine is actively transported into the thyroid cell, and then it's oxidized to iodine. So remember, it was iodide form, that kind of ionized form, gets into the thyroid cell, and then it becomes iodine. And the thyroid gland actually has to trap about 60 micrograms of iodide per day to make the thyroid hormones. So a fair amount. And then the next thing that happens once iodine's in the thyroid cell, first it binds to thyroglobulin. So, and then this creates that monoiodotyrosine. So what I'm showing you here is this guy. Monoiodotyrosine, this is the thyroglobulin, here's the iodine. And then so instead of like drawing out that whole complicated structure, I just call it thyroglobulin plus 1 iodine. So again, that makes that first precursor monoiodotyrosine. Then another iodine is attached, and then that becomes diiodotyrosine. So again, just in case anyone's confused, now we've just made this one. So the thyroglobulin plus 1, 2 iodines. And then in order to make the active versions of the thyroid hormones, the body basically condenses either 2 of the DITs together to make T4, or alternatively, it will attach 1 of the DITs with 1 of the MITs. So 1 of the diiodotyrosines to 1 of the monoiodo, then to make T3. And yeah, that's basically what it is. So the T3 and T4 is really just named after how many iodines are on it. And interestingly, T3 and T4 both circulate around, but we have much higher concentrations of T4 in our blood. It's actually 50 times higher than T3. But interestingly, this is kind of like T4, you can kind of see it almost as like the storage form circulating around in your blood. But then more of the active form, or they can both do the job of typical thyroid hormones, but it's been shown that T3 is much more functionally potent than T4. So basically it can do the job a little bit more effectively. So what happens is, even though this is circulating around at higher concentrations, the body will turn it into T3 when it wants to do its job, basically. So most tissues can deiodinate T4 to T3. Because remember, the conversion is just cutting off this iodine, just removing that. Other than that, they're pretty much exactly the same. And most tissues can do it, but the body will basically send most of this to the liver to basically convert T4 to T3. And that's just done by 5-deiodinase. Yeah, and then most of the T3 that you find is, done, synthesized by the liver or deiodinated. So I don't really understand. I couldn't figure out why the body would have so much circulating as T4 when it doesn't really use it that much. It doesn't really make sense to me. It seems like it'd make more sense to just have it all in that active form, but for some reason it doesn't. So yeah, remember T4, kind of the storage form. It's kind of floating around waiting to get activated, and then it's deiodinated into T3, which is the active form. So just looking at the RDAs for this, it's the same for males and females, 150 micrograms per day. And really this was entirely based on the level of intake necessary to prevent goiters. Yeah, and so basically we can talk a little bit about goiters and everything we kind of know about that. So you probably knew before taking this class that people that had iodine deficiency would develop goiters. So kind of those big, I have some pictures of it in a little bit. Yeah, basically those large growths around the neck, which is basically the thyroid gland like puffing up pretty much. So why would low iodine intake result in goiter formation? Why would your thyroid gland puff up like that if you're not getting enough iodine? So it's kind of interesting, and it's not super straightforward. Like, it took me a while to kind of, I think it's kind of hard to figure it out. So let me just walk you through kind of how this all happens. So if you have low iodine intake in your diet, then obviously that would translate into less thyroid hormones being made. So you'd have less T3 and T4 just circulating around. And then what happens then is the pituitary gland, so basically the brain, senses that there's not enough thyroid hormone circulating around. So it then releases thyroid stimulating hormone, TSH. So it starts releasing a lot of TSH, and that basically is it's basically a hormone that goes to the thyroid and says, okay, you need to make more thyroid hormone. Unfortunately, the thyroid gland can't make more thyroid hormone because it obviously needs iodine to do that, and there's just insufficient amounts coming in. So then what the thyroid does, which is kind of interesting, is it starts to enlarge, and basically it tries to become kind of like this big, kind of huge, like net almost. So it enlarges to kind of become a net, so then more blood basically kind of travels through it, or it gets more circulation so that it can trap more iodine. So yeah, the whole reason that goiters are formed is so basically the thyroid can act as a net to filter more blood to try to trap more iodine in the circulation. So yeah, that's how it all happens. And iodine deficiency is still definitely a pretty big, like, worldwide problem, primarily in parts of Asia, Europe, Africa, Australia. So the darker, basically it's more severe iodine deficiency where it's kind of darker purple. You can treat goiters, so they're not a permanent thing. If you do supplement at the RDA level, the gland will return to normal size in a few months. It depends, how big it was to begin with. If it's small, it'll probably go back down in like a month or two. And if it's really large, it might take more than 3 months, but it is reversible. So it's not a permanent thing. Once you finally get enough iodine, it will go back down. Yeah, and it can be pretty cheaply addressed by just iodizing salt. And it does, still affects about 2 billion people worldwide. It used to be a pretty major problem in the US as well. So these are just some photos I found of kind of goiters in the US. I'm not sure, this is kind of what came up as an early 1900s goiter. That almost looks more like cancer though, but it's a pretty extreme version of it. But yeah, this is definitely a pretty typical kind of well-developed goiter. So in the early 1900s, particularly in the Great Lakes area, so right around here, like, anything Michigan, Indiana, Illinois, that type of thing, Wisconsin, all of that was, there was tons of people that had goiters at that time. So yeah, roughly about 100 years ago. And they were trying to figure out, they knew that putting iodine in food would help kind of reverse this. But they were trying to figure out like what food can we put it into, and then they realized, well, salt is great because everyone uses it and it's really cheap. So that's why it was basically a professor at the University of Michigan in the 1920s that suggested iodizing salt to treat goiters. And then by 1924, all salt production, for the most part, included sodium iodine. So it's almost, sometimes it's hard to find salt that is not iodized. And if there's no iodine in it, they usually make it pretty clear on the label. But the majority of the salt that you'll buy in the grocery store has iodine in it. So TUL is set at 1,100 micrograms per day. There's been reports of acute toxicities, which basically somebody was taking like 2 grams, which is huge considering that, yeah, the RDA is 150 micrograms. Excuse me. So yeah, you get like burning sensation in the mouth, throat, nausea, vomiting, and then it can involve, it basically obviously can eventually lead to death. But some people do take kind of regular, kind of chronic amounts of this, chronically high amounts. So it's been reported that somebody was taking 1,800 micrograms per day for 4 months. I'm not sure why, but this would actually, chronically high intake above the TUL can actually result in thyroid problems. So it kind of ends up messing with your thyroid gland, and it can lead to hypothyroidism or hyperthyroidism. So yeah, definitely not a good idea to supplement with this. I've looked for iodine supplements in like pharmacies and stuff, and I've never found any. So we get so much from salt that it's not really an issue. But yeah, so if anyone sees any, yeah, let me know. All right, moving on to our very last nutrient of the whole class, fluoride, which is actually not even an essential nutrient. So kind of ending on a bit of a weird note. But as we all know, fluoride is used to basically promote the health of like bones and teeth, specifically teeth, and basically lower the amount of cavities we get. But it is not essential. There's an AI set for it, but again, it's not something that your body needs to live. It just kind of promotes health. You can kind of see it that way. So just to kind of show you a little bit of the nomenclature first, fluorine is that gaseous kind of state, basically the gas form of fluoride. Whereas fluoride is that ionized, kind of the valence state of -1, and that's the one that's kind of found in foods. It's usually bound to like peptides, that type of thing. A key source, or where we basically get all of our fluoride, is from drinking water, and it's because water in the U.S. is fluoridated for the most part. It really varies county by county, but a lot of counties try to fluoridate their water to 1 milligram per liter. So that's when they do fluoridate water, that's what they're shooting for, basically that amount. So water would provide about 0.24 milligrams of fluoride per cup. And then we also get it from toothpaste, obviously. So kids can actually develop like a toxicity if they eat toothpaste. So when I was little, I definitely, like when my mom would buy like bubblegum flavor or whatever, I'd totally go to town on that and like eat too much of it. And then, yeah, so that can actually result in like toxicities. But so yeah, we mainly get it from toothpaste and drinking water. So history of fluoridation, none of this really started until kind of like the 1950s. In the 40s, they discovered that inverse relationship between fluoride intake and lower levels of cavity development. And then it was in the 50s that drinking water first became fluoridated because of this discovery. So food sources, we don't really get it from many foods. I've had this question, so I just kind of wanted to point this out. Food content is generally really low. So usually it's less than 0.05 milligrams per 100 gram of the food. And then the food also, it really depends. The fluoride content of the food depends on the use of fluoridated water during processing. So were they making it with fluoridated water? But you can get like a little bit in like the bones of marine fish or like tea, but yeah, not super amounts. Basically, again, we get it mainly from water, and mainly from like accidentally swallowing toothpaste, basically. Just to kind of show you who's fluoridating, in the US, so it'd be the red one here, it's about 60 to 80% of counties fluoridate. And again, it's all based on county. And then if you look kind of the rest of the world, a lot of it doesn't fluoridate. This one country in Africa really does, though, for some reason. But yeah, other than that, it's kind of variable. So looking at the percentage of the U.S. population receiving fluoridated water, so here in Illinois, so Cook County does fluoridate. So if you're living here or if you're born here, you've basically had fluoridated water your whole life. Oregon does not. Oregon's one of the ones that barely any counties fluoridate. Interestingly, California, only like 20 to 40% of the counties fluoridate. So it really varies kind of from where you came from. But it is basically related to cavity development. So counties that don't fluoridate, there tends to be more cavities in those counties. So just kind of looking some absorption and just basically going over that. When you do consume fluoride from food, it's usually attached to peptides. And then so you'd want to release it, typically that's what we always see. You release it from the peptides via proteases or HCl, and then you get the free fluoride. And we pretty much absorb a lot of it. Remember, because we're mainly getting it from water. So we absorb most of our fluoride in the stomach via passive diffusion. And then we also absorb some of it in our small intestine via passive diffusion as well. So pretty kind of basic way. Yeah, nothing too complicated there. And we absorb about 100% of fluoride from water and about 50% from food sources. And then after the fluoride's absorbed, it's delivered to tissues, primarily bones and teeth. So we basically consume it in water, and then it's incorporated into bones and teeth in both the amorphous rapidly exchanging pool and the crystalline slowly exchanging pool. This isn't super important. Basically, yeah, gets in our bloodstream and then is incorporated into bones and teeth that way. So the key function of fluoride, we always hear that it's good for our teeth, but why? What is it doing that's good? So what it does in the crystalline pool, so again, you drink the water, it ends up kind of going into your bloodstream, and then it basically gets into your bones. And then what your bones are doing is it's actually attaching the fluoride onto hydroxyapatite. So where did we see that before? If you look back at your like calcium, phosphorus, and magnesium lectures, we talk a lot about hydroxyapatite because that's one of those compounds that is incorporated into bone, and it's basically kind of filling up the holes in that kind of protein bone lattice. So when fluoride attaches to hydroxyapatite, it actually makes hydroxyapatite you can kind of see it as being like stronger. When it attaches, it's called fluorohydroxyapatite. And the reason that it's good for teeth is that fluorohydroxyapatite is less acid soluble than hydroxyapatite. So if you live in a county that doesn't have fluoride, obviously you're still making hydroxyapatite. That's incorporated into your teeth just like it would your bones. Your bones and your teeth are made pretty much the same way. But yeah, if you live in a county where you do fluoridate, then what's going to be mainly incorporated in your teeth is fluorohydroxyapatite. And then just a bit of background, you probably know this, but just remember cavities are made not because there's bacteria kind of like eating away at your teeth. It's actually the bacteria eat sugars that are kind of left on your teeth or after eating. And then it's a little gross, but like the bacteria excrete this really kind of acidy kind of excretions, and it's actually like the excrement of the bacteria that's causing your teeth to kind of decay. So what they found was this fluorohydroxyapatite compound is basically less acid soluble than hydroxyapatite. And then I also get a lot of questions about, well, do you have to drink water for fluoride, like does it have to go like into your body and then get incorporated into hydroxyapatite? Or like why are they putting it in toothpaste? Will the fluoride actually become a part of hydroxyapatite, like just if it's put like right on your tooth? And yeah, there are studies showing, the reason they started doing this is because there are studies showing that even just putting fluoride or doing like fluoride rinses and stuff at the dentist, it can get incorporated into hydroxyapatite just by that way too. So it's not just by drinking water, but also, yeah, fluoride rinses, and then also just putting it in toothpaste and kind of exposing it to teeth that way. So this is just a graph to show you that basically the DMFT is kind of a fancy way of saying cavities. And then this is percentage of fluoridated drinking water over the years. And just to show that as they decided to start increasing or adding fluoride in different counties, the amount of cavities do go down. So again, there's that kind of inverse relationship. When people have fluoridated water, their levels of cavities in those counties do go down. The main route of excretion is urine. So that just happens also by passive diffusion. And then again, fluoride's not essential. You can definitely live without it. It's more of kind of just like a health promoter. So they've only set an AI, and there will probably only ever be an AD. RDA probably will most likely never be set. And the AI is mainly just set because of that evidence based on that inverse relationship between fluoride intake and lower levels of cavities being developed. And the main advocates for this, obviously, would be the American Dental Association. So they've done most of the studies in this area, and they've kind of, they showed a lot of kind of pretty good, strong studies, and that's why a lot of counties are deciding to fluoridate water now. So there's no deficiency disease. Again, it's not essential. The only thing is, if you have lower levels of fluoride, you might have an increased risk of getting like cavities, basically. But definitely it's not an essential nutrient. Toxicity is set at about 10 milligrams per day. So we typically take in, with the amount of water we drink, about 3 to 4 milligrams per day, just to kind of put that TUL in perspective. If you have, there's been some reports of like, I don't even know how people did this, but they took in 10 grams of fluoride. Typically acute toxicity of any nutrient results in like nausea, vomiting, and death. But things that you probably are more common is just chronic toxicity. This really happens when kids like eat a lot of toothpaste, and what they get is mottling of teeth. So I had some friends that actually, I remember when I was younger, that had this. So whenever you see these kind of like yellow, this kind of pattern develop on people's teeth, and it's usually seen in kids, that's because of fluoride toxicity. So it actually turns into this yellow kind of stain. But if you're eating like too much or getting too much fluoride from toothpaste or wherever you're getting it from, not only will it kind of like stain your teeth, but it can also result in impaired kidney function, muscle function, and basically problems with nerve function as well. All right, so we are all done. I'll do kind of a mini review. So we'll just do like half of this. And then, again, feel free to ask me any questions about the macrominerals or microminerals. Just email me as you start kind of studying and going over these slides. So let's just do, the last 4 that we did. So last lecture and this lecture. So what are the food sources of selenium and chromium? So remember, selenium is mainly like meat, and then chromium's found everywhere, even on like chrome-plated toasters and stuff like that. But it's found in like meat and fruits and vegetables and all that type of stuff. So all of these, well, I guess let's do these 2 as well. Where do we get iodine from? So remember, high sources of that, the main source was salt. So table salt's the main place that we get it. But then also fish, so particularly seawater fish. And then where do we get fluoride from? Mainly from like water and toothpaste. And again, it's not essential. All right, so functions. All of these just have one function, which makes it pretty easy. So what's selenium? It's in an enzyme. What's that one enzyme? So it's glutathione peroxidase. And remember, that helps neutralize peroxides. And then chromium, what's the one function of chromium we talked about? So that was the insulin receptor activity, basically helping insulin to bring in more glucose. So it's kind of almost like an insulin sensitizer. It upregulates the insulin receptor. And then iodine, what does iodine do? Makes thyroid hormones. Fluoride, probably knew this already, helps promote integrity of bones and teeth. Is there a deficiency of selenium? So remember, that's the Keeshan's disease with that Coxsackie virus. So it's kind of specific to having low levels of selenium in soil, and then also in combination with having that virus present. How about chromium? That one's related to the function. So people can become kind of insulin resistant with lower levels of chromium. What happens if you don't have enough iodine coming in? So that's when you get a goiter. And then in terms of deficiency for fluoride, there's no deficiency state. So let's just finish off toxicity. What's toxicity of selenium called? Selenosis. So that's like that. It was kind of like nondescript, like general weakness, and I think it was like nausea, vomiting, that type of thing. Chromium, is there a toxicity? Nope, no toxicity there. What happens if you take in too much iodine? That's the one where you basically start developing thyroid problems. And then lastly, what happens if a kid eats like too much toothpaste? What's the main kind of clinical thing? Tooth mottling, or the state's called fluorosis, but yeah, tooth mottling, that kind of like staining, yellow stains on the teeth. All right, great. So that's the last lecture for the class. All the lectures from calcium all the way up until fluoride will be included on the exam. So I'll send out an email clarifying all that. But yeah, just basically these 9 lectures will all be on the exam. And please email me if anything's not clear. The tutor is also available to help, so you can contact her and set up a tutoring appointment too. Great. Well, it was really nice teaching you guys. I'm sorry that the last little bit has been just me sitting alone at home. But yeah, good luck on the exam, and I hope you all have a great summer.